Hey, today we're going to look at our last integration technique for quite some time. It's called partial fractions. Take a look at this integral. Well, it turns out that no technique that we have learned so far will allow us to solve this integral. I mean, you might try substitution, that would be a good guess, but it just doesn't work, and then you're just stuck and there's nothing that you can do. On the other hand, take a look at this integral. This integral is pretty easy. The first one is obviously an arctangent, and the second one, after you do a little bit of substitution, you can find some version of the natural log there, and you end up with 5 times the arctangent of x plus 3 times the natural log of the absolute value of x minus 2 plus a constant. And what's the point? The point is that these are the same integral. It's not hard to show. Take 5 over x squared plus 1 plus 3 over x minus 2 and combine them. Well, first you need a common denominator. The common denominator would be x squared plus 1 times x minus 2. And after you multiply the first term by x minus 2 over x minus 2 and the second term by x squared plus 1 over x squared plus 1, you get this expression here. And then there's just some simplifying to do. Expanding the numerator and distributing the denominator, you get this, which after you finish simplifying gives us 3x squared plus 5x minus 7 all over x cubed minus 2x squared plus x minus 2, which if you'll notice is exactly what we had over here. Okay, it's not hard to take an expression like this, do a little algebra, and come up with an expression like this. It's also not interesting or useful. If we had the expression like this in the first place, we would just integrate it. And so the idea behind partial fractions is, how do you take an expression like this and sort of work your way backwards until you get an expression like this so that you can integrate? And there are a bunch of steps, and I'll lay them out for you carefully very soon. But first, why don't we try, this precise example where we take this expression that we started with right here and figure out how to turn it into this one right here. The idea is, or the important thing to emphasize here, we're not really talking about calculus. This is an algebraic technique. We are asking, how do you take this algebraic expression and turn it into this algebraic expression right here, so that you can do some calculus on it. But to say it again, partial fractions is an algebra technique. Some algebra that you can do to make some integral easier to handle. Okay, so we're starting with the integral of this rational expression. And before we do any calculus, off to the side, or in this case underneath, we're going to do some algebra to try to rewrite that rational expression into some form that will be easier to integrate. And the first step is always going to be to factor the denominator. Now, in this case, we've got a cubic polynomial in the denominator, and you might not remember how to factor a cubic. Don't worry about that for now. We will review it at some point. It factors as x squared plus 1 times x minus 2, as you can easily check by multiplying those two things together. And the next step is to say, well, if I have a fraction whose denominator is x squared plus 1 times x minus 2, then it must have come from adding two fractions together whose common denominator was x squared plus 1 times x minus 2. And what are all the possibilities? Well, one of them could have had a denominator of x squared plus 1, and the other could have had a denominator of x minus 2. That's really the only way in this particular situation to get something with a common denominator of x squared plus 1 over x minus 2. And we're going to rely on the fact that in the original rational expression we were talking about, the degree of the numerator is 2 and the degree of the denominator is 3, meaning the degree of the numerator smaller than the degree of the denominator. If it turns out that that's not the case, then there'll be some things that we can do at the beginning, but in general, we need to at least do some work to get it so that we're working with an expression where the degree of the numerator is smaller than the degree of the denominator. And that's going to have to be the case with the fractions that we add together to get this expression as well. And what does that tell us? That tells us that the degree of the numerator in x squared plus 1 has to be smaller than x squared. So it's a linear numerator. So at worst, it's something like ax plus b. And the degree of the numerator in the fraction that has the x minus 2 in the denominator has to be smaller than x, meaning it has to be just some constant. And so it's just some number c. And it's very common. The convention is to use capital letters for the constants in these partial fraction problems. So that's what I'll be doing. So a, b, and c here are some real numbers, some constants. And then the trick is to figure out what those constants a, b, and c are. And the biggest problem with solving for them in the current form is that I have these horrible rational, this horrible rational equation, which is difficult to solve. In other words, it's the denominators that make this confusing, and so we can do some work to make them go away. You have to be a little bit careful. There's no magic to make them go away. It's actual reasonable algebra. Here it comes. You can always multiply both sides of an equation by the same thing, and that's what we're doing here. We're multiplying both sides of this equation by x squared plus 1 times x minus 2. That will make all the denominators go away. You have to do the multiplication carefully. On the left, you just get 3x squared plus 5x minus 7 because the x squared plus 1 times x minus 2 in the denominator cancels with the x squared plus 1 times x minus 2. On the right, you have to distribute. In other words, you're multiplying x squared plus 1 times x minus 2 times both of these terms, ax plus b over x squared plus 1 and c over x minus 2. And then various things cancel in each of the two terms. In the first term, the x squared plus 1's cancel, leaving us with x minus 2 times ax plus b. And in the second term, the x minus 2's cancel, leaving us with c times x squared plus 1. And so now we've got some equation that we have to solve for a, b, and c. As with so many of the things that we do, there's more than one way to do it. Let's make a little room and look at the first of them. In the first method, we simplify the expression on the right and rewrite it as a polynomial. So do all the distribution that you need to do and all the simplifying that you need to do. After you distribute, you get this expression here, and then combining like terms, you get a plus c times x squared because we had an ax squared and a cx squared. We get b minus 2a times x because we had a negative 2ax and a bx, so I just rewrote them, negative 2a plus b, same thing as b minus 2a. And then what's left is the constant terms, which were c and negative 2b. So I put those together, that's the constant term. And these two expressions are equal. And so the way this method works is it says, well, these are the same expression. And so this a plus c here, we know what it is. It's a 3. Has to be. It's the coefficient of the x squared term. Same idea. What's this b minus 2a? Well, it's a 5. Has to be. It's the coefficient of the x term. And what's this c minus 2b? Well, it has to be the 7 because it's the constant term. And that gives us these three equations. A plus c equals 3, b minus 2a equals 5, c minus 2b equals negative 7. 3 equations in 3 unknowns. We ought to be able to figure them out. There are lots of ways to do these, and you've probably learned some clever way with matrices that you are welcome to use if you like. I'll do it the most straightforward, sort of least sophisticated way, which is a technique known as substitution. You solve for one variable in terms of some of the others, and then just plug in to the other expressions until you've figured out all the values. Here's how it goes. I can certainly write from that first equation, a plus c equals 3, that a is equal to 3 minus c. And then I can plug that into the second equation, which becomes b minus 2 times 3 minus c is equal to 5, because a is 3 minus c. Simplifying that gives me that b is equal to 11 minus 2c, and now I can plug that into the third equation. So I have c minus 2 times 11 minus 2c is equal to negative 7, because b is 11 minus 2c, and when I solve this, I should have a value for c. And indeed I do. After just a little bit of algebra, I get that c is equal to 3. I can now use that value to go back and find the values of a and b. In particular, from this equation right here, I get that a is 3 minus c, and c is equal to 3, and so a is equal to 0. And from this equation right here, I get that b is 11 minus 2c, and since c is equal to 3, that gives us that b is equal to 5. And so just to recap, we've figured out that a is equal to 0, b is equal to 5, c is equal to 3. And if we move back up to see why we care about that, it's because that tells us how to rewrite our expression. The original expression is 0x plus 5 over x squared plus 1 plus 3 over x minus 2, or just 5 over x squared plus 1 plus 3 over x minus 2, like we already knew it was. All right, that was the first method. Let's go back down and see if we can work out a second method. And it starts with the same work up to where we have cleared the denominators and come up with this expression that 3x squared plus 5x minus 7 is equal to this stuff on the right over here. But then it uses the idea that if these two expressions are equal, then they're equal for all possible real numbers x. And there are some real numbers x that you could plug in that would make this much simpler. In particular, if you look at what happens at x equals 2, then you get plugging in x equals 2 on the left, 3 times 4, because that's 2 squared, plus 5 times 2 minus 7. And on the right, you get 2 minus 2 times some stuff. I don't care what it is, because 2 minus 2 is 0, so that term is going to go away entirely, plus c times 2 squared plus 1, which is 4 plus 1. Which, after you do the arithmetic, simplifies to 15 equals 5c, and you automatically get that c is equal to 3. So that was a lot easier than the work that we had to do to find out that c was equal to 3 through method 1. And then you keep going like that. Turns out there's another value of x that we can pick that will make this a little bit simpler. If we look at what happens at x equals 0, then on the left we just get negative 7, and on the right we get 0 minus 2 times a times 0 plus b, so that's the nice part, that a is going to go away. And then we already know that c is equal to 3, so there's a 3 there, times 0 squared plus 1. And when we simplify, we get that negative 7 is equal to negative 2b plus 3, which after a very little bit of algebra gives you once again that b is equal to 5. We still don't know the value of a, and it turns out in this particular situation that there is no particularly clever value of x that we can choose that will just have a fall out for us like we did with x equals 2 and x equals 0. But here's an equation where we already know what b and c are. They're just constants and we've figured them out. So there's only one unknown. We can pick any value of x, and that will give us the value of a. So we may as well pick one where the arithmetic is easy to do. Let's look what happens at x equals 1. On the left, you get 3 times 1 squared plus 5 times 1 minus 7. And on the right, you get this expression that I've written here after filling in that b is equal to 5 and c is equal to 3. So all that's left is to do a little bit of easy arithmetic and algebra. And I had to squeeze it into the bottom there a little bit. Poor planning on my part, but you get the same answer we did before, that a is equal to 0. And when you're working on a partial fractions problem, you can use either of these two methods to figure out the constants a, b, and c, but it will often turn out that one of them is significantly easier than the other. And more often it will turn out that this second method is easier than the first method. You should probably get comfortable with both of them because you don't want to do more work than you have to. Okay, I promised you a set of steps. In the next video, we'll look at a bunch of examples, but for now, we'll just describe the process a little bit more carefully than we did in the one example that we've done so far. So suppose you have some rational expression of the form p of x over q of x, where p and q are both polynomials. How do you reduce it into its partial fraction decomposition? This first step is sort of the unusual case. You won't run into this too often, but it's worth stating anyway. If the degree of the numerator is larger than or equal to the degree of the denominator, then you have to start off by dividing the numerator by the denominator. And what do I mean by that? I mean polynomial division. Divide p of x by q of x. So we'll do an example at some point to remind you how that's done. What you'll end up with then is some polynomial, which you can integrate directly, plus some remainder, which is a rational expression where the degree of the numerator is smaller than the degree of the denominator. And so usually we won't have to worry about this step, but there it is. If you have to, then you have to. The second step, which you'll always have to do, is factor the denominator. Occasionally you'll be given a homework problem where that factorization is handed to you, so lucky you. But in general, you need the factorization of the denominator in order to proceed. So that's our first general step that we will always have to do. Where to go from there is really the step that's the doozy, and it's got a number of parts. And the first part is, if there's some linear factor of the denominator, such as x minus a, then there's some part of the decomposition that looks like a constant over x minus a. And the capital A and the lowercase a have nothing to do with each other. I'm just saying there's some constant in the numerator, and this is part of the partial fractions decomposition. This generalization of that step before it confuses people. I'm going to go over it a little bit slowly. The cubed part is arbitrary. It could be to any power. But just to pick a specific example, suppose you had an x minus a cubed as a factor of the denominator. Well, where could that have come from? It turns out, if you're adding fractions together and the common denominator is x minus a cubed, then there might be some number over x minus a, there might be some number over x minus a squared, and there might be some number over x minus a cubed, because the common denominator of a over x minus a plus b over x minus a squared plus c over x minus a cubed, the common denominator of those three terms is x minus a cubed. And so in order to make sure you pick up all the pieces that might have gone into getting that common denominator, you need all three of these terms. An a over x minus a, b over x minus a squared, and c over x minus a cubed. And of course, if it was just x minus a squared, there would only be two terms here. If there was an x minus a to the 94th power as a factor of the denominator, you'd have 94 terms here, each ramping up the denominator by 1 degree. What we've looked at so far is what happens if you have linear factors of the denominator, or different powers of linear factors in the denominator. Another possibility is you could have quadratic factors in the denominator. And in particular, you could have irreducible quadratic factors in the denominator. Like we saw in the example we just did, we had an x squared plus 1 as a factor of the denominator. You can't factor x squared plus 1 into the product of any two linear factors over the real numbers. And so if you have an irreducible quadratic factor of the denominator, then you get a term in the decomposition that has that denominator with some linear numerator, ax plus b, where a and b are constants. So the only time you have an ax plus b or cx plus d or anything like that in the numerator is where the denominator is an irreducible quadratic. And the final case is just the generalization of this case like we did with the linear factors. It looks ugly, but it's really not any worse. If the irreducible quadratic factor of the denominator shows up to some higher power than 1, like in this case I've chosen 3, well then, just like we did for linear factors, you need multiple terms in the partial fractions decomposition. How come? Because if there's an ax squared plus bx plus c all cubed in the denominator, if that was the common denominator of the combination of some fractions that you were adding together, well, what could they have been? They could have been some linear term like ax plus b over ax squared plus bx plus c, and then another cx plus d over ax squared plus bx plus c all squared, and then finally some linear term over the same thing cubed. And so you put all those things together, what's the common denominator? It's ax squared plus bx plus c cubed. So not that that happens so often, but it could happen. And so now you've got all the possibilities. This is how you set up your expression. Here's my rational expression. What is it equal to? Well, a bunch of stuff over a bunch of different constants or linear terms over a bunch of different denominators. These rules guide how you construct that original equation that is so important to making progress. What do you do next? You do a bunch of algebra, using either our method 1 or our method 2 that we looked at, to find the constants A, B, C, D, whatever you've got. You figure out what those constants are from the equation that you just set up. We saw 2 ways to do it. And then depending upon what you were asked to do, you might be done. In other words, follow these steps and you will have taken a rational expression and reduced it into its partial fractions decomposition. So you've rewritten some rational expression in some completely equivalent way as partial fractions. And if that's all you were asked to do, then you're done. Often this shows up in the context of a calculus problem. That's why we're talking about it, in which case there's one last step. If you were bothering to compute the partial fractions decomposition so that you could compute an integral, then once you've done it, don't forget to integrate. Integrate the results, and then you'll have your answer. Okay, you have all the theory that you need now about partial fraction decompositions. There will be a second video that just does examples, but there's nothing else new to learn, just a lot of practice required. So start the homework if you like. If you get stuck on anything, don't worry, it's not due quite yet, and we will do a bunch of examples. Don't forget my admonition that there is no magic involved. You really have to do the algebra carefully, in particular at the step where you are eliminating denominators. People tend to notice a pattern and just jump right to some expression which is completely wrong. Be careful. The way you're doing that is multiplying both sides by the same denominator. So, do that carefully and you should be in good shape. So, all right, we'll do a bunch of examples in the next video. We'll certainly talk about it in class. Have fun. See you soon.